So, shall we start? Hi, everybody. So, we ended up here last time. So, we started with the convolutional neural networks. We just got the idea how the convolution works. And we do know what is a convolutional layer right now. Yeah. So, here we have the last slide, which we used or we studied last time on Tuesday. And here what we have is a multi-channel convolutional layer, getting a multi-channel input and then converting it into a multi-channel output. So we got here one input, which is a tensor, 3 by 32 by 32. So do you have any idea what are those numbers? What is 3? The number of channels is, for example, an RGB image. What is 32 by 32? The image size, right? So this is 32 pixels by 32 pixels. So you have 3 maps. Each of them is a channel, and each of them is 32 by 32, right? And then you do it by, you just get this guy, and then you convolve it by this filter. So it's written 4 times 3 times 5 times 5. Do you have any idea what is 4 here? The number of channels at the output, which is actually the number of filters we have in this convolutional layer, correct? And then 3, what is 3? 3 input channels. Is the number of input channels or the number of channels you have in each of those filters, correct? And then 5 by 5, what is that guy? That is the filter size, exactly. So you're going to get your 32 by 32 image once again. So you get your 32 by 32 image. So here is 32, here is 32. We have 3 of them stuck to each other. So we have 3 of them. This is the number of channels that we have. This is 3. And then we get a filter, which is a small one. So the filter is 5 by 5, but it has the same number of channels, which is 3. So this guy is now something like this. So it's again 5. It's very bad. By 5. 5 by 5, and it has the same depth, which is 3. And we have 4 of them, right? So we get the first one. We just slide it here. We get the first output channel. Then we get the second one. We do the same thing. We get the next output channel till the last one. Yeah? And then once we are over with everything, what we're going to do at the end, what we do on this one before we pass it to the next layer, we do the activation, right? Meaning that we get ReLU function, for example, and pass every single number in this output tensor through that activation function. And now we have the activated output of the convolutional layer, and then we can pass it to the next layer, correct? Great. So this is the idea of convolutional layers. So now you have the perfect idea, and you do know the practical form of the convolutional layer. Then after that one, let's just go to the next part or next component of the CNN, which is the pooling layer. So what is the pooling? So we talked about the pooling in our dummy example. What we did, we just simply looked at the map, and then we took the maximum value. And I told you this is what we call it max pooling, right? So with the pooling, we usually, the main purpose that we do it, there are 2 main purposes. The first main purpose is to, if we want to talk about intuitive application of this pooling, is to just get rid of the jittering in the output of the convolutional layer. So when you get a convolutional layer, it's just going to focus on different parts of your image. And this could very well be very spiky. It just changes in value quite rapidly. And then the thing that we can do, we can use pooling to just somehow filter that jittering out of the output of the convolutional layer. This is one purpose that we are doing. The other thing is that we want to somehow, I haven't mention it here directly, but we usually in practice what we do, we use convolution by stride 1. And once we have done this, then we do pooling plus a stride more than 1. And by doing that, we get rid of a bit of features that we don't want. Okay? So pooling has mainly two purposes. I mean, you want to somehow smooth out your output, plus you get rid of the non-relevant features. So this is one thing that you do, but one other thing that is like implicitly being done by pooling is that you are improving the shift variance. And do you remember what was shift variance? Do you have idea what is shift variance that we are looking for? So, sorry, shift invariance. Do you remember what is shift invariance? So do you remember the first example we had with the MNIS in the background, right? And we were, I mean, FNN was not, the MLP was not shift invariance, because when I give it the MNIS image somewhere else in the background, then it was going to fail, right? I mean, if I shift the image or the pattern inside the input, then it's not robust against that shift. So in convolutional neural network, we really want to get shift invariance. So I mean, there are some literature talking about the degree of shift invariance that your model has and things like that, but we're not really going to talk about it. I mean, this is not that crucial anymore in the context that we are, or in the state that we are now with neural network. But shift invariance simply means that if you give an input and you do any sort of geometric variation into it, then the output of your neural network is somehow still valid. So it's robust against any sort of geometric changes inside your input. So this is one of the purposes that pooling is going to serve, but you don't see it implicitly. I mean, it's just, sorry, you don't see it explicitly. You see it implicitly. So there are two main forms of pooling, or two main famous forms of pooling, which are max pooling and mean pooling. This is the typical one that we use usually in implementation. And let's see what they are. So the first one is max pooling, and as the name says, you simply look into a window, and then you pull out, you take out the maximum value. Like, for example, here, this is your input map. Again, you assume that for now, you assume just you have one single channel in the input. So this is your input map. It has n different rows and m different columns. And then what you want to do, you want to just apply max pooling on it with the filter of size L by L, I write here, right? So here in this image, L is simply what? What is L in this diagram? It's 2, right? So the filter is, again, exactly like the filter you have in convolution. So it's a square matrix, and then that L should be definitely less than m and n. And then here it's 2 in this particular diagram. So I'm going to look at this diagram. I'm going to look at these 4 numbers, which are within that filter of 2 by 2. And then I take the maximum value. So I'm going to get this guy. I give it to the maximizer. So it looks at these 4 different numbers. And then it writes down the maximum value here. So y hat 1, 1 is simply the maximum between those 4 different values. So among y1, 1, y1, 2, y2, 1, y2, 2, the maximum one, whatever it is, it's going to sit here. Clear? Now, I'm going to slide it again exactly like what we did in convolution. So when I want to just write down the next guy here, I'm going to slide that one right. And once I slide it right, again, I look at that window and I take the maximum value and put it here, right? And I keep on going like this till I just fill out the whole output map. Clear? So same thing that you do. It's exactly the convolution. You're going to see it shortly, that you are pretty much doing convolution. The only difference is that when you are just sliding your filter, you don't do any linear combination. You simply take the maximum value, which is by somehow a linear combination. But the value, the weight of the maximum guy is 1. The weight of everybody else is 0, right? Correct? OK. So that is max pooling. And one thing that is important with max pooling is that once we do max pooling, we need to save the index of the maximizer. Like, for example, here, say this y hat 1, 1 was y 1, 1. If this is the case, when we are finding this guy, we should also pay attention to the index, or we should save this, because we're going to need it when we want to backpropagate. You're going to see it. Okay? So just let me give you one example. Look at this guy. So this is the input filter. And what I want to do, I want to just do max pooling. Okay? So I'm going to make an agreement here. And my agreement is that, say my filter is 2 by 2, as you see here. And I make an agreement. I say the index of this guy is 1. This is 2. This is 3. This is 4. Okay? And one thing, I mean, in this slide, you see this, the font of this 1.3 is different from this 3. You see it, right? You can see it, right? So this is index. This font is index. This is value of the input. So don't get confused. Okay? So this is not the value of a filter or something. So it's just a filter for max pooling. You put it right on that guy, and you look at the maximum value. So the maximum value between these 4 different values, that is 3.2. So I'm going to write down 3.2 here at the output. Clear? And then I'm going to save the index as well, right? So I'm going to say the maximum value is at index 4. So I made this agreement that index 4 is for this, right bottom corner entry. So I'm going to call it index 4. Yeah? Clear? Now, what's going to be the output of the next one? Since everybody is sleeping, so maybe it's going to be good. Index is going to be 3, and the value is going to be 3.2. Great. So when I come here, it's going to be 3.2 exactly, and the index is 3. The next one is going to be 2.1, because, I mean, between these 4 numbers, 2.1 is the maximum value, and the index is 3, and you can keep on going like this. So you can try it later on. So every point, like here, 4.3 is the maximum value, so I'm going to save it here, and then I'm going to keep the index because I'm going to need it later on. Okay? So with max pooling, you have one map at the output, and of course, I mean, behind the scene, you have one map which is saving the indices. Okay? Everybody's clear? Great. Okay, so that is with the max pooling. You can do, instead of max pooling, mean pooling. And mean pooling simply means that instead of taking the maximum value, you simply compute the average of the things within the filter. Okay? So this means that I'm going to look at these 4 different guys, and then I'm going to just take the average value of them, meaning that I just sum them up divided by 4. Right? So you get these guys, you just compute the mean value, you write it down at the first index. Then you just slide it next. Then you're going to, again, look at this one. You just compute the mean value, you write it down there, and then you complete the whole output map. Clear? Now, this guy, is it different from convolution? Is it a different operation as compared to convolution? No. This is exactly convolution. So what are the values of the filter? 1 over the number of things, LS squared, exactly. Yeah? So basically what you could say that mean pooling is a convolution where you have uniform kernel. And by uniform kernel, I simply mean that all the weights are 1 over the dimension, LS squared here. Clear? So what I could say here, for example, if I am doing mean pooling, I am taking this filter, I look at this guy, and then I am going to average them out, just sum them up divided by 4, and I write it down here. And then I'm going to slide it next, again look at that window, and then I average everything there, I write it down there, and I can complete this, this output map by going through that. Okay? And if instead of that, I simply just assume that I have a filter whose weights are 1 by 4, and I just convolve this filter with this input, I'm going to get exactly the same thing. Yeah? I mean, it's basically the same thing, right? But you are not going to just think of a general weight now, correct? So it's a kind of uniform weight, predefined, and you do know it. So clear about the mean pooling? Great. So that's it. And one more advanced idea is that you just don't use mean pooling or max pooling. You can just use a general pooling. Okay? So this is a general form of a pooling layer, where you have one particular function. So you have this function pi here. This is taking again this, for example, submatrix. This is a small matrix, L by L dimension. And then it just gives you a value R, a real value within R, within the real set. Okay? So it's going to get the matrix. Then it's going to compute one particular value, and then it writes it here. Yeah? And you can just, again, fill everything out by sliding over your input. Yeah? And that particular pi, it could be even itself a separate neural network. For example, I can, instead of pi, I can define my pi to be like this. So I'm going to start with the one input, second input, and so on till input L is squared. Okay? And then I give it to one hidden layer. This is one hidden layer, so I connect everything to the hidden layer. Then again, I connect this guy to another hidden layer, and so on till I get to the last hidden layer, and then I give everything out to a neuron with activation F, right? So each time I go over, I trained this guy before I had, and now I fix it there, and then I just go over every single sub-tensor or submatrix. I give those values as the input, and then I see what is the output, right? And then I write it down there. I can do it, yeah? So the whole thing here, from here to here, this is the pi function that I am showing there, yeah? Yeah. And if you really want, you can even train this guy the same time that you are training your CNN. This is even possible, right? We don't do it in practice then. We don't get into that. If you get into a very, complicated problem, you might think of it, but it's not going to gain you a huge thing. But you can, yeah? Clear? So this is a general form of pooling layer. And then if you want to do pooling with a stride, I guess everybody has the idea how you can do it, right? So you basically jump with that stride, correct? So you simply just, for example, if you want to do with the stride 2, instead of just sliding one step forward, you just slide 2 steps forward. One thing is that usually with pooling, we don't do fractional strides. So if you remember, we could do fractional stride, meaning that I could have a stride half, right? And if I have a stride half, what does it mean? Yes, upsampling with factor 2 first, and then I do the convolution, correct? And if I want to do it with a stride 3/2, or 3 by 2, 1.5, I still can do it. I do upsampling with factor 2, I do the convolution, then I do downsampling with factor 3, yeah? We talked about this. So you could potentially do it with pooling, but we usually don't do it. So this is one point. So the main reason is that upsampling only just when you do upsampling before the pooling, then you are just adding zeros, right? And then pulling out of zeros is not going to help you that much, right? Especially if you are doing, for example, max pooling. Yeah? Obviously, that zero is not doing something useful for you. So yeah, one particular example is max pooling. But integer stride is usually used in pooling. And what you can think, again, you can think that you have pooling with stride 1, and then after that you have a downsampling, right? And usually in practice, in most neural networks that you implement, usually you do this stride more than 1 in the pooling layer. So you do convolution with the stride 1 up to a point, and then at some point you have too many features. You want to get rid of some of them. And then you do pooling plus some stride. Okay? And then you get less features. And you gradually do it until you just get into the number of features you are comfortable with. Okay, so that's usually the case, and yeah, as I told you, yes, the integer stride, we usually leave it for the pooling, and then we do the convolution with the unit stride. Now, let me see what I wanted to say here. I don't know what I want to say. Oh, yeah, okay. I think I told you this before, but you might wonder that if we are going in practice to do pooling always after convolution. So when we started, I told you like a classical CNN is that you do convolution, then pooling, again you repeat it and you keep on doing it till you are over. But if you get a bit more advanced, like for most advanced or say benchmark architectures, you don't do pooling immediately after every single convolution. So in practice, you can do multiple convolutions, like VGG16 that we're going to see today. It does it so. So you do multiple convolution layers, and then at some point you just do the pooling, because at that point you want to get rid of some features, some unnecessary features, and also smooth out your feature space. And then you again keep doing that. Okay? So it's not a kind of some sort of say a must thing that you should follow every convolutional layer with a pooling. So this is not necessary. And yeah, that's it, I guess. So one other thing is that most poolings, they do not have learnable parameters. So this is what you saw here. So max pooling, mean pooling, they don't have any parameter that you learn them, meaning that they just get updated in the training. This is one other point. But this one that I showed you here, it could have potentially some parameters that you can train. Yeah? Maybe for some application it becomes useful. Okay? I don't know. But in general, they don't have. And the filter size of the pooling in general can be different. Sorry. So filter size of the pooling can be in general different from your convolutional filter, but usually in practice they are the same. Yeah? But it's not a must again. You know, you can always play with all of them. They're not going to gain you something huge, but you can do it. Okay? So that's it. So we do know what is convolution now. We do know what is pooling. And then the next thing that we need to do is just flattening. But I guess this is more than obvious for all of you, right? So what we do in flattening, we basically get the last layer. So we look at the last layer, which is the last one after all those convolutions and poolings. And that one is what kind of object? Is it a vector? Is it a matrix? Is it a tensor? It's a tensor, right? So say I started with an RGB image. I had 3 channels. Then I did a convolution. I got 10 channels. Again, I did a convolution. I got, I don't know, 20 channels. I did a pooling. And then again, convolution. I got 80 channels. And now at the end, I have 80 channels. So it means 80 different matrices next to each other, right? And then I have this much of matrices, and all of them have lots of numbers, right? Now, what I'm going to do, I'm going to make an agreement. So I say, OK, I start from this one in the tensor, and then I go this way, for example, however you want. And I'll put them in form of a vector. Clear? So I'm going to look at the first guy in the first map in the top left corner, and then I write it as the first entry of my vector. Then the next one, second entry, next one, third entry, and I go on till I'm over with all things in the tensor, right? So I finish the first map, then I go for the second map, and so on till I'm finished with the last map, and then I have this very huge vector, right? But that vector, I can give it now into a feed-forward neural network. This is what we call it flattening, because we get the tensor, we don't do anything. We basically just deform it, reshape it into form of a vector, right? And this is what we call it flattening, because we are flattening that tensor into a one-dimensional array. So if this is our last convolution or pooling output, then we're going to have lots of channels, and each of them is a particular map. And the thing that we are going to do is to just do the thing that I told you. So I'm going to just form it in the form of flatten it into a form of a vector, and then I give it into my feed-forward neural network. And after that is exactly what we had before, right? So it's going to go pass through multiple fully connected layers till it gets to the very output. Okay? Now, say I have k different channels in this last output, and each of them is n times m map. Then what would be the dimension of the input of that feed-forward neural network? What is it? Product of all of them, right? Because I have k channels, each of them has n times m map. So if I write one map, it's going to be n times m vector. And then I put the next map below that and so on. So I'm going to have k times mn different numbers, and all of them are saved into in form of a vector. And this is going to be the input of my feed-forward neural network. Everybody's clear? Yeah? Great. So we do flattening, we pass it, we get the output. And what is the output if, for example, this is a classification problem? What is it?
Probability of each class.
Yes, is the output, for example, of the softmax, and is the probability of each class. Exactly. So you start with one image and say your classes are cat, dog, frog, 10 different animals. And then you do convolution on that image, pooling, convolution, pooling, convolution. You get lots of feature maps. You just flatten them, pass them through maybe 2 different hidden layers. And finally, the last output layer going to have 10 different outputs, which you just pass it through softmax. And it's going to give you a probability of 10 different classes, which each class just representing one of those animals. And when you make that trained, then if you give a dog image into it, then the probability of the dog class is going to be the highest one. And you're going to understand that is the dog. Okay? So that's it with respect to flattening. So I guess now you have the idea how the CNN works in general. But any questions before we go further with the deep CNN? No question? Great. OK. So now we can look at the convolutional layer to be simply a feed-forward layer, okay, as we had before. So when I started the chapter, I told you CNN is a feed-forward neural network, which is using, in addition to those fully connected layers, in addition to them, it's using convolution and pooling, right? And you do know convolution and pooling, but you might say why you indicated that this is a feed-forward neural network. I mean, obviously, this is just feeding everything forward, right? So you're just passing everything forward. That's right. But you actually can think of it as a kind of giant FNN, giant MLP. How you can think of it that form, just let's look at one layer which is doing convolution, okay? So if I want to do convolution of this 9-pixel map with this 4 weighted filter, 2x2 filter, what do? I'm going to put that filter on the first part. I multiply everything to this, and then I sum them up, right? That's correct? OK. Now, if I look at this filter values, W1, W2, W3, W4 as weights, and then I look at x1 to x9 as my inputs, then what I can do, I can put my inputs from x1, x2, so on till x9. So these are the input nodes. And then I would say, OK, x1, x2, x4, and x5 are going to compute the first entry of the output map, right? So I'm going to connect x1, x2, x4, and x5 to the first output of the output map. So z1, z2, z3, z4 are the entries of the output map. When I do the convolution of this guy with that one, with the stride one, without zero padding, I'm going to have 2x2 feature map. And I simply mean this. So this is z1, z2, z3, z4. OK? And z1 is the convolution of this filter with that part, which is going to be those weights multiplied with those inputs and then summed up. Correct? Then the next thing, I'm going to slide, and then I'm going to multiply x2 to w1, x3 to w2, x5 to w3, x6 to w4, right? And then sum them up. I can again say, OK, x2 here, multiply with w1, so the red guy is w1. x3 multiply with the blue one, which is w2, and so on. x5, green one, which is w3, and the last one, x6, which is multiply with the yellow weight, which is w4, correct? So you can do it for every slide that I do, right? So I can put it here. Again, it's going to be a bunch of inputs connected to Z3, and I can put it at the last point, and it's going to be a bunch of inputs connected to Z4, correct? Now, what can I say about this whole thing at the output? So I can look at this whole convolution process as this connected layer, right? This feed-forward layer. So in this layer, every particular x is or every bunch of x's are connected into one z. And then once I compute, at z, I'm just going to just sum them up after multiplying with the weights. And after that, I'm going to activate it, which is the activation after convolution. Correct? So that convolution plus activation is basically one of the layers that you had in feed-forward neural network before. Everybody is seeing that? Now, what are the weights of that layer? The weights inside your kernel, exactly. So instead of doing those slides, you basically could compute everything in this form. Yeah? But that one is more intuitive, more illustrative as this one. But what you are basically doing is this guy. Now, this guy, as I told you, this is pretty much the same thing that we had in chapter 2. But there are two major differences as compared to that one. We didn't consider this particular form. Do you know what are those? Do you see the differences with the fully connected feed-forward neural networks? It's not fully connected. Great, because x1 is not connected to z2, for example. Yeah? So in fully connected layers, we connect every input to every neuron, right? So this is one difference. The other difference. The weights are shared, exactly. So when you do fully connected, you connect x1 to z1, and you give it one weight. But when you want to connect x to z2, you give it another weight, right? So you have so many weights in between. But right now, you have only 4 weights. So some of those links are sharing weights. Clear? So what you can say that this is basically a feed-forward neural network, a feed-forward layer. And the main difference is that they are, first of all, sharing the weights, and they are also not fully connected. This is what we call it locally connected feed-forward layer. Okay? So CNNs are locally connected feed-forward neural networks with shared parameters. Correct? OK. So that's the idea. What about the pooling? The pooling can be seen again the same way. So what I can say, for example, if I'm doing max pooling, I could say, OK, say I am doing max pooling. This is a dummy max pooling, but say I am doing with this 1 by 2 filter, I am max pooling over this input. So I'm going to look at y1, y2. I take the maximum, right? So I can look at y1, y2, y3, and y4, all of my inputs as different nodes. And then the first 2 are connected to the first neuron. And the neuron is going to just take the maximum value. Again, when I slide it down, the 2 other inputs are going to be connected to another neuron, which is again going to take the maximum value, right? So again, what you can say this pooling layer is also a feed-forward layer with locally connected architecture. Yeah? So it's not fully connected anymore. And it has its own specific activation, which in this case is maximization. Clear? So CNN is a special case of what you had before. Yeah? But this particular special case is working very well when it comes to visual applications. Okay? Great. So now, the next thing that I want to tell you before we start training this convolutional neural network is receptive field. And I somehow informally introduced them before to you. So what is a receptive field? Like, as I told you, when you have your image and you do your first convolution, every particular output in your feature map is looking into a part of that input image, right? So that part, it's called receptive field, right? But you can define this receptive field not only for the first feature map. You can define it for any feature map within your neural network. Okay? So for example here, say this is my input, the first guy, and then the next one is the feature map that I am computing by doing a convolution on this first image. So the point is that that particular red pixel is only looking into this part, right? And that one is the receptive field of this pixel. But what about the next layer? So say I give this new map, this feature map, into another convolutional layer, and I compute the next feature map, right? Now, what about this feature map? If I look at one particular pixel of this guy, one particular entry inside this feature map, this is being connected to the previous feature map within a specific receptive field, right? And that one is, again, every single of them is connected to one receptive field. A union of all of those receptive fields is the receptive field that this guy is going to look into. Correct? So this one is only looking into this top left corner, but this one is pretty much looking into all of it. And this makes sense. But it's not looking at it immediately. It just waits for the previous features to be processed, right? So every layer that you go forward, every single pixel, every single neuron in your convolutional layer is extending its receptive field. Yeah, you got a question? Yeah?
In the last layer, I was wondering, there's lots of Y. They are zeros?
Sorry? No, they're not zeros. I'm not showing them. I mean, if you add zero padding, you can just fill them out. It's just intuitive.
So when we use this kind of convolution and something like that, we try to just decrease the dimension. Am I right? Yeah, so if we start from the first layer, we are...
Not necessarily. I mean, we're going to see it in the slide. I mean, not necessarily when you do convolution, you are reducing your dimension. I mean, you can keep the dimension, as we talked last time. With zero padding, of course, of course. So you keep zero padding here. So if you pad, I mean, here is 3 by 3. So if I just pad 0 all around this this input map, then this whole feature map going to be exactly of the same size. And I do the same on the next feature map, and I keep the dimension. So I can keep the dimension without any harm. Yeah? But the point is that every single neuron, as you go deeper and deeper inside your neural network, is looking into a larger and larger part of your original input. Correct? So now what kind of feeling we could have about this is like you have image of an animal, right? And you want to know whether it is a cat or a bird. Yeah? And then there are a bunch of features. I mean, of course, you as a human being can detect it. But when you want to train a machine to understand it, it needs something with values, right? So what is the key differences between bird and, I don't know, cat? Maybe is that, yeah, birds have beak and then the cat has nose, yeah? So nose is one thing, ear is one thing, eye is one thing, correct? So it's going to scan it in the first feature map, and then it just write down a bunch of features. And then, again, that guy is going to just scan these features, and it's just extending the receptive field into the previous image. And then you're going to get more things, right? And then these features gradually are going to somehow give you, look at the whole image and going to tell you, OK, the feature regarding the nose is, for example, 1 here. the feature regarding the ear is 1, the feature regarding the eye is 1, but the feature regarding the feather is 0. The feature regarding, I don't know, beak is 0, and so on. And then you say, the machine actually, the neural network says, OK, so this is a cat, because it obviously has ear, has nose, has eye, but it doesn't have any feather. OK? So between bird and cat, it's going to be cat. OK? So this is what the receptive field is doing for you. So as you go inside further, you are looking into more part of the image. But if you just, from very beginning, tell your neural network to look at the whole image and tell me whether it has feather or not, it's going to be a very hard thing for your neural network to do. Yeah? So those feature extractions are going to help you to just get better idea about these properties of your image. So formally defining the receptive field for one given particular neuron inside your convolutional layer, the receptive field is the region inside your input where that particular neuron is looking into. And first of all is for the very first convolutional layer, that receptive field is simply the part that your filter is just looking into. So it's very, very well specified with your filter size. But as you go deeper inside your neural network, it's going to get harder for you to specify that. But you can simply say that as you go harder, it's going to just increase in size. So this is one obvious thing. And of course, the receptive fields are some depending on the filter size as well. So the filter size, if you increase the filter size, you are just in each layer, you're just looking into a larger part of the previous layer, meaning that as you go through your depth, you're just going to increase your receptive field faster, right? Whereas if you just keep your filter very small, then this increase in the receptive field size is going to be slow. Clear? Yeah? Now, you might wonder, OK, why I'm talking about this receptive field. Because that one, as I told you, is going to give you a bit of intuition. And this intuition is very important when you want to design a neural network, a convolutional neural network. So let me just give you one funny example. So it's not, I mean, it's not a very, detailed example, but it's very intuitive. But it's going to give you a sort of comprehensive idea about the receptive field and what you need. So say that you are giving this image to your neural network, and that neural network, what it wants to do, it wants to just classify it, which is a cat, of course. But the cat is somehow very cute in this case, with a hand on her head. So we might, the neural network might do a mistake, right? So it might just say it's a human being because there is a hand there. So it needs to just do it in more details, correct? So how we can do it, the thing that we are going to do, let's just look at two different convolutional layers. So we have the first convolutional layer, which I am showing its Fisher map with this orange color. And then the second one, which, after doing the convolution and activation, I am again doing another convolution. And this is the second Fisher map, right? Now, if I look at this guy, so this particular pixel inside my feature map, and I am doing the convolution with this particular filter, then what I can say that this guy is looking into this part, right? And the next one is going to look into that part. The next one is going to the next part, and so on, yeah? But when I talk about this guy, that one is going to expand, right? Because this one, when I do the convolution with this particular filter, again, 2x2 filter, is going to look into this 2x2 part of your feature map. And this guy was looking into these four. The second one was looking into the second four. The third one is looking into the third four, and so on for the last one, right? So that yellow part is the receptive field of this guy in the second layer, yeah? And you can see that as I go further, that receptive field is going to expand more and more. And at some point, it's going to get the ear of the, for example, cat into it, right? So when it gets the ear of the cat, it doesn't see the hand of the human still, right? So it's going to get the feature of that ear, correct? So it's going to tell you, oh, an ear is here, right? Then it's going to expand gradually. It's going to see, I don't know, the snout of this cat, and it says, okay, there is a cat-like snout here, right? And then gradually it goes up, and then it's, okay, there is also a hand there, yeah? But before it gets to the hand, it has just detected so many features of the cat that has made you convinced that it's a cat, not a human being, right? Whereas if you want to just look at the whole receptive field, whole image at the very beginning, you're going to say, okay, hand, snout, ear, so it's going to make it a bit hard to detect. Correct? Yeah. So what I'm saying is not very concrete, but I hope that it just gives you the idea how this convolution is gradually building those features for you. Okay? Any questions? Great. So if you got no question, then let's just use this intuition to build a kind of idea how we can design a convolutional neural network if we really want to do a very fine job, okay, a very deep neural network, and we want to just do a very, for example, good classification. So what we have concluded here is that deep CNNs are gradually just extracting features of the output, and in the very first layer, we are going to just look into the, some receptive field, and gradually in every layer we are just expanding that receptive field, right? Now, the receptive field, as I told you, is proportional to the filter size, okay? Now, if I want to design a deep convolutional neural network, and I want to make sure that in every layer that I am just going forward, I am not missing any feature of the image, what would be your suggestion? Should I just take a very large filter and simply just stride over the whole image, or should I consider a smaller filter? No, say I don't want to miss any feature. I mean, I don't know what is inside the image. I should keep it small, right? Because at the beginning, I have no idea about that cat or hand of human being, right? So what I'm going to do, in the very first layer, I'm going to use the small filters. And these small filters is going to just give me large feature maps, meaning that I make sure that I am just looking into very tiny bit of the image in every slide that I go on. And one thing else that I know is that as I keep on going through depth, I am not crazy in increasing the size of the receptive field, right? So I'm looking at the very tiny bit of the image first, and then in the next layer, I just slightly increase it, and each time I'm just capturing the whole features inside that, correct? So this is what I do in the first layers. But at some point, my receptive field is large enough that every neuron is pretty much looking at every part of the image, right? Correct? It doesn't matter how small my filter is. At the very end, I'm going to look at some layer. I'm going to look at the whole input, right? Then what should I do at that point? So at that point, if I'm going to further process that feature map is not going, the next feature map is not going to expand my receptive field. The only thing that it's going to do is going to just process the features that I have already extracted. Yeah? And at that point, I'm going to increase the size of my filter because I don't care anymore about the receptive field. And also, I'm going to maybe drop some features because, like using a stride more than one, because, all parts of the image has been repeated in many of those features that I have collected. Clear? So as I go deeper, I'm going to increase the size of the filter because I basically don't want to look at the image anymore, and I just want to process those features. Clear? So one thing else that I'm going to do is that I am going in the initial layers, I am going to use small number of output channels, meaning that I'm looking at a 3 by 3 image. Say, let's talk about a very dummy example. So RGB image, 3 channel image, RGB image, and then I keep the channels 3 because I'm just looking at the image, right? At some point that I get into a place where I have the feeling, okay, I have scanned every part of the image up to this point, because receptive field of this layer is pretty much for every neuron is the whole image at the input. Then at that point, I start to increase the number of output channels. Why? Because I want to somehow decompose the features that I am extracting. Okay? So again, this is a very dummy example, but I somehow want to have at the very end tiny small maps, a lot of them. And one of the maps is telling me, like, there is a nose here. One of maps is telling me there is a hand here. One of maps telling me there is a feather here, and so on. Okay? So about the number of channels, I start with a small number of output channels, and I gradually increase it. Okay? Everybody's clear? So you got the idea. I mean, at the end of the day, these are hyperparameters. You are going to choose it by your own. But in practice, having this idea in mind, it makes you decide for a better choices of those hyperparameters. Yeah?
I think what happens is that at some point you have a small feature map and
Yes.
through it. I think
We have small, no, we have large feature maps because we have small filters, right? Okay, with the small filters, I have large feature map. And I am not saving them in a very large number of channels, meaning that the number of output channels is small. And I keep on doing this up to a point where I have the feeling like now every neuron in this convolutional layer is looking at pretty much every part of my input image. Now what I can say like the features that I have extracted up to this point, every single of them is a combination of all the features that I have in the image. So I'm pretty much over with that. The next step is that I want to somehow make it understandable for my feed-forward neural network later. So I'm going to increase the size of filter, meaning that the feature that I extract next, the feature maps are going to get smaller, right?
you want to increase.
If I increase the filter size in one layer, the output feature map is going to decrease.
That's right.
Correct? So at that point where I have the feeling like I have scanned everything in the input, I'm going to increase the filter size, meaning that if I compute one particular map, that map is smaller now, right? But now, in order to grasp all the features that I have extracted up to this point, I'm going to increase the number of channels. Okay? And then the ideal case is that at the very end, I have lots of channels, each of them very small map. And every single of them is looking into one particular feature in the original input. And that one is understandable now for my feed-forward neural network. Yeah? So this is the whole idea that I'm getting rid of that shift variance or dependency on the spatial part of the image, for example.
But I think before when we were doing multiple channels, the filters applied on each channel were the same, or were they, am I wrong?
Yes. No, it's not the same. There are different filters with the same number of channels. I'm going to show you VGG16 now, and then you're going to get the idea. But I hope you got the feeling like as you go deeper inside your CNN, the number of channels that you should see on your feature tensor should be more, and the size of filter could gradually increase. Okay? So now let's just take a look at this VGG16, and then this guy is going to tell what I wanted to tell you more clearly. So you're going to see some numerical example. So what it does, probably if you just search VGG16 architecture, you're going to see this guy. Different versions, but usually look like this. And every of those blue, maps, every single of them is one convolutional layer. Okay? So it's not a real map. I mean, it's a tensor, actually. And that is a convolutional layer. So you have two convolutional layers here. Then these red guys, they are pooling. So as you can see, the convolutional layer is big, is the same size of, I mean, pretty much the same size of the input image. But then the next guy, which is the pooling, the red one, is smaller. So this means that I have increased the stride when I change from that convolutional layer to that pooling layer. Okay? No stride, I mean, in this particular one, stride is 2. And then again, I do 2 convolutions with the stride 1. Again, I do a pooling with the stride 2. And then I again do 3 convolutions. And then I do a stride, pooling with the stride 2. And I keep on going till I get into those green guys. So these green guys are actually the fully connected layers. And these ones are the ones that have, I mean, when I get into this one, I have a huge number of channels. So the number of channels, as you can see, it is 512. Each of them is a 7 by 7 map. Okay? Just grasping one tiny particular feature of my input image. Okay? So let's look at it here. I mean, I'm not sure if you see the numbers, but I can see it from here roughly, and I can tell you. So this is how the VGG16 look like. And given the things that we studied up to this point, you can now understand every details here. So what it does, it's going to get one image as the input. And this is written here, 224 times 224. 224 times 224 times 3. So what does it mean? 3 is the number of channels. Okay, so I usually write it down here, but in this image is here. Okay, so 3 is the number of channels because the image is RGB, right? So RGB image here, and then what is these? What are these two guys? The size of the image. So it's 224 by 224 pixel RGB image. Clear? Okay. Now, this image is taken from the ImageNet dataset. Do you know, have you ever heard of ImageNet dataset? So do you know how many classes are there? 1,000. Okay? So it's a very big dataset. I mean, we're going to see it in chapter 5. It's a very big dataset. And then there are images of 1,000 different things. You know, animals, obstacles, vehicles, things like that. And 1,000 different classes are there. Okay? And now, every single image is of this size, 224 by 224 pixels. Okay? And RGB. Now, this guy is going to go in the first convolutional layer. And the number that you see under that is the output size. Okay? So the size of the tensor at the output. So here is 224 times 224 times, I think 64. Oh, I have it here. 64, right. So the next layer is 224 times 224 times 64. And this is given by a filter which is 3 by 3. Okay? Now, can you first of all tell me, when I have written here 3 by 3 filter, what does it mean? Is the filter simply a matrix? No, it's a tensor. And what is the number of channels in this tensor? 3, exactly. Because here I have 3. I have 3 here, so I should have 3 here as well. This is not written here, but you can simply infer it. Clear? Now, what you get at the output is 224 times 224 times 64. What does it say? You have 64 different output channels, meaning that you have 64 different filters, right? So it's not only one filter, it's W1, W2, till W64, right? Now, filter size is 3 by 3. Your output size, I mean, input was 224 by 224. It's still 224 by 224. What do you think about this stride and zero padding? Stride is 1, obviously, because we have not changed the order, right? 224 is the same. And in order to keep it exactly the same, should I do a zero padding or not? Yes, I should do a 0 padding 1. Again, it's not written here, but you can simply infer it, right? Now, the next guy, this one here, this one here, this is written 224 by 224 by 64 again, meaning that I am going to do exactly the same thing. So I'm finished with these 64 filters. Again, I'm going to give this output into another guy, and that is, again, of the same form. So there are going to be a new bunch of weights, so W1 maybe hat till W64 hat. Yeah? These are not the same filters. Of course, they are new filters, right? And 64 of them.
Times 64, not times 3.
Exactly. This is the next thing we wanted to talk. So what is the dimension of this one? So it says it is 3 by 3. But what should be the number of channels that it has? It should be 64, because it's going to get convolved with this guy, right? So this guy has 64 channels. So this one should have also 64 channels. You got the idea? Clear?
No, I mean the output of the layer that we.
Oh, sorry. This is 64. Sorry. Yeah, this is 64. Exactly. So again, this is 64. And after doing that, you are going to give it into a max pooling layer. And the max pooling layer, as you can see, it is 112 by 112 times 64. So does it have a stride? Yes. And what is the stride? 2. Exactly. So it has a stride 2. It does 0 padding 1. And then it's going to give you 64 channels at the output, because in max pooling, you're not changing the number of channels, right? Yeah.
I don't understand. The true first convolution layer, do we have the stride?
Sorry?
Do we have the stride there?
No, the stride is 1, because the dimension is not changing.
Yeah, exactly. Yeah. So this is 1, and the output is 0. Yeah.
What do you mean by output is?
Some other, when we have a stride 1, also we have some 0 padding.
Of course, of course. We have 0 padding all around it. Exactly. Yes. So 0 padding, padding length is 1.
Yeah.
And then filter size is 3 by 3, so you're going to keep the dimension as it was. So then when you do pooling, then you're going to get, you do the pooling, of course, on every single map, right? And then you're going to get, still you have 64 different maps, but now the dimension of every single map is halved, right? And then you get this guy, again, you repeat the same thing. So as you can see here, now I am going to have the output of this next convolutional layer is 112 times 112 times 128, meaning that I am increasing the number of channels at the output, right? So the number of channels at the input here is 64. Now the number of channels at the output is 128. So I have 128 different filters. Every single of them is 3 by 3 by 64. Clear? Now, you're going to have this one, then you're going to get into the next one. So it's exactly the same dimension. So stride is 1, 0 padding length is 1, and then you're going to again do the pooling. Yeah? So you get rid of a bunch of features you don't need. Clear? Yeah.
Why do you need to increase the number of channels?
Increase the number of channels because you want to somehow push every particular, say, macro feature into one channel. Yeah, okay. So, it's just intuitive discussion, but if you look at the image of one creature, animal. So that animal has specific parts, So you can think of the union of all parts of all animals, right? So snout, ear, eye, hair, feather, I don't know anything, leg, hand. And then when you look at that image, you could say, okay, there is a kind of hyper feature. Let me call it hyper feature, macro feature. And that macro feature is the type of snout, right? So how much that snout is the snout of a dog or snout of a pig, So I can give a number for each of them, So what I want to do, I want to just make as much as those hyperfeatures, and every single of these hyperfeatures is somehow saved in one of those maps. Okay? So I am going to gradually increase the size or the number of channels that I have, because I want every single of them to look into a more specific into one particular hyperfeature. Okay? And then the more I have, the better I can decide. Yeah.
It means that, for example, one channel just looking for the eyes, one channel just looking
Somehow. But it's not happening from very beginning. By doing that, you're making your neural network to do this.
That's why, for example, we have 64 channels in the first step, then it's
Yes. Yeah, to increase it, exactly. But you need to keep this first 64 because you want to do the convolution enough so that when you are at this point and you are just going to increase the number of channels and reduce the number or the size of every map, you have the feeling like every single neuron in the very last convolutional layer has taken a look into a good part of the input image. Yeah? So you cannot do it immediately, because if you do it immediately, you probably miss some of those hyper features. So again, you can see here we are doing same convolution, then we do pooling, then again we come here, we again increase the number of channels, so now we double the number of channels, is 256, and then by doing that we are going to just again repeat the convolutions and then pulling, convolution, pulling, convolution, pulling up to this point. So at this point I have 512 different channels, but every single of them is very small. It's just 14 by 14, right? And hopefully every single of those 14 by 14 images or maps are going to just focus in one particular hyperfeature that I want. And then again I do the pulling, and then I start to do the flattening. Okay, or I start giving it into a fully connected neural network. So here, the output of my last pulling is 7 by 7 by 512. And if you multiply 49, 7 by 7 is 49, 49 by 512, it's going to be 25088. Okay, 25,088. And this is exactly the size of your input to your fully connected layer here. Okay? And then after that, you're passing it into a dense layer. By dense, it simply means fully connected. The same thing you had in chapter 2. And this one is your first hidden layer. Your first hidden layer has 4,096 neurons. So you see, you're now greatly reducing the size of the features. From 25,000, you are coming to 5,000. And then again, you have another hidden layer with the same size. And finally, you have one output layer with 1,000 outputs. Why 1,000? Sorry?
Like a vector activation function, something like that?
Yes. So what is this number 1,000?
Number of
Classes that you have. Great. Yeah.
I have a question for
Sure.
the number of convolutions we perform per layer. How
Yeah.
do we decide how many convolutions we
Yeah, this I cannot tell you for sure. Yeah, so you need to get a sense about this by practicing, but like rule of thumb, the more the better.
Okay. And then for the flattening of
Yeah.
the feature map of the feature tensor, I would say. So we do that once we have a lot of channels, so that we make sure that all these channels capture as many features on the picture as we can.
Exactly.
Right. And then we flatten.
Exactly. Because then you say that this is something that my MLP, my fully connected network, can understand. If I give the original image to it, it doesn't understand. Yeah? So, and then finally you give it into a softmax and gonna specify you the chances of each class. So if you simply just sum up all those layers that you have, I mean, you have 2 convolutional layers, 2 convolutional layers. I mean, after each of them, you do a pooling. 3, 3, 3, and then finally you have 3 fully connected layers. If you sum them up, it's going to be 16, and this 16 is actually why we call it VGG16. So Video Graphic Group in Oxford University just proposed it with 16 layers. Yeah. It's crazy, yeah, but think about it. If instead of, I mean, that image I showed you that this is locally connected with shared parameters. Just think about it if you wanted to do it with a fully connected neural network. The number of parameters that you would have had is like crazy. I mean, by orders of exponent more than this one, right? So it is actually doing you a lot of good. So it's just reducing hugely the number of features that you have. But as I told you at the beginning of semester, I mean, the number of features that you are dealing with is always in the order of 10 to the power 5, 6, 7, or even more. Yeah, you had a question? Okay. So, yeah.
The flattening, is it a 2x2 vector?
Yeah, you just make it a vector. Exactly.
No, I'm just wanting to understand if it's a one-dimensional vector or a two-dimensional.
No, it's just a one-dimensional vector. Yes. Yeah, exactly. Like the one you give to MLP. Right. Yeah. 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 Here. Yes. Here. Yes. Is the second hidden layer, yes. Yes, you have here 2 hidden layers, 1, 2, right? So after flattening, you pass it through 1 hidden layer, then the output of that hidden layer is given to the second hidden layer, and then this is the output layer. But if you need, you can give more hidden layers, of course.
So the output hidden layer is actually first time decrease the number of vectors from 4,000, more than 4,000 to 1,000 first, then activate it to the softmax.
Yes, exactly. So yeah, so you get this 4,000 something, so 4,099. So you get this one, and then you just pass it through 1 linear layer, which has 1,000 output, and then you just pass it to softmax. No. So everybody's clear? Machine learning model. So basically, in any convolutional layer, we have a bunch of convolutional. In any convolutional network, we have a bunch of convolutional layers. We do have a feed-forward neural network also at the very end, and all of them have weights and biases, right? And then the thing is that we want to just compute the loss between the output of that convolutional neural network and the ground truth, the label that you have, the true label that you have inside your data set. And then next thing, we want to find the weights in a way that it's going to minimize this loss. Okay? So the things that we are going to take as the parameters or weights are, of course, the weights of the filters of those convolutional layers, so the weight and biases of the FNN. And if we have anything in between, like the advanced pooling or anything that we add, we could have those weights as well here. So if you do batch normalization, then those parameters of your batch normalization are also going to show up, right? So if you want to just look at it very generally, so we usually have a data set of this form. So usually the input now is a kind of tensor, right? So X is a sort of tensor type data point, 3-channel RGB image, right? So X is a tensor, and then V is its corresponding label, right? So this label could be a scalar label, integer label, or it could be a vector, right? For example, it could be one hot vector representation, correct? X is image of a cat, RGB, V is the class of cat, right? So that's it. And then the thing that you are going to do, you first of all send this particular guy through your convolutional neural network. So since I'm going to use lots of Y and X's here, so I just use theta to be the very output of my neural network so that you don't get confused, okay? So theta b is what your convolutional neural network is going to give you at its output when you just give the tensor xb to it, okay? And the thing that you do, as usual, you are going to just compute the loss between this output and the true value, the true label that you have. And then say you have b different values inside your batch. So b different data points inside your batch. You are going to just average those losses. And you try to find the weights and filters that are going to give you the least possible loss, correct? So if we want to solve it, of course, we are going to do gradient descent. I mean, you can do a stochastic gradient descent by just breaking it down into mini batches, things like that. So everything as before. But the whole issue is that we need to know how to go forward and backward over that neural network. Because once you can go forward and backward, you're able to just compute all the gradients that you want, and then everything is as before. Yeah? So the whole story is, again, to get back on the computation graph and then try to just move backward from the loss or risk that you have computed towards the very input. Okay? So some part of it you already know how to do it because we had FNN, right? Feed-forward neural network. You know how you can pass backward, for example, through a linear layer or activation, right? But some other things you don't know, like if you have a pooling or you have a convolution, mainly these two things, you don't know how you can move backward. I mean, of course, you can always model it as a fully connected layer, and then you try to make a kind of one-to-one connection and do it. But it turns out that these backward passes are much easier than you can think. Okay? So say that I have passed forward this guy, and now we want to move backward. The only thing that I need to do is to just be able to just move backward over every single of these passes. And some of them, as I said, we already know. Some of them we don't know. So one just quick recap for the forward pass. I mean, this is more than obvious for all of you. If you do a forward pass, you get your initial tensor. Then you just do the convolution, activate it. So you do the convolution, you get Z1, right? This is linear convolution. So this is before activation. And then you do activation, you're going to get Y1, right? You just pass every single guy here through ReLU, for example. And then you do a pooling, say, for example, and then you get Y hat 1. And you repeat this. You give Y hat 1 to another convolution, you do another activation, you do another pooling, and so on. And then finally, you just flatten and then give it to your feed-forward neural network. So now, if we do the forward pass, so you remember that when we talked about the backpropagation, we said if we want to be able to compute the gradients, we need to go forward, meaning that we need to compute every single variable in between, right? All of those z values, y values, we need to know them, right? So when you are doing it with CNN, it's the same thing. You just pass it forward, and you compute every single neuron in between. You need to know all of those maps, the value of all of those maps and channels, all of them, right? And you also need to know all of the values in your feed-forward neural network. And you're going to save them because you're going to need them for backpropagation. And now that is over. Now you want to just move backward, meaning that you have ended up, or you passed one. Sorry. So you pass one particular input tensor, and then it's just gone through the whole network. And then you finally got your theta at the output, and you're able to compute the loss, right? Now, once you compute the loss, can you compute the gradient with respect to theta? Of course, yes, because you do know what is loss in terms of theta. For example, that is cross entropy, right? You can simply compute it, right? Now, if you want to get from theta to the input of your fully connected network, can you do it? Can you? So what do I mean by that? So I have a convolutional layer, then I did some pooling, again I did a convolution, again I did a pooling, and then finally at this point I just did the flattening. So this guy is flat. And then I give it to my first hidden layer, second hidden layer, and then this is my output. So here is a softmax, and here is my theta. And from that theta, I can compute loss, correct? So I can get from loss back to this guy. You told me yes, and I'm sure you do know it. Yeah? So I can get back from loss to this theta. I can compute the gradient of loss with respect to this one. Whatever here is in between, up to this point, which is the input of my feed-forward neural network, this is all things that we had in Chapter 2, correct? So meaning that you do know how to get back from this one to the input of your softmax, how to get from this one to the input of your first or last hidden layer, the previous hidden layer, up to this point, right? So you do know how to go there. So I'm not going to repeat this for you. You already know how to get into the input of your feed-forward neural network. OK? The fully connected. Now, from now on, the story is new. OK? So we are going to backpropagate up to the point where you get to the input of your feed-forward neural network. And at that point, the thing that we are going to do, we are going to get to redo whatever we did in flattening. OK? So meaning that if, just a dummy example, if I had two, say I had two maps. OK? This is map 1, this is map 2. And each of them had 4 numbers. So here it was z1, or sorry, I have written here y hat. So y hat 1, y hat 2, y hat 3, y hat 4, and so on till the y hat 5, and so on till y hat 8. OK? When I do the flattening, so here is, I do flattening. So I'm going to put them in the form of a vector, right? Correct? Now, when I'm backpropagating, I am going to compute the gradient of the loss, or the partial derivative of the loss with respect to y1, partial derivative of the loss with respect to y hat 2, and so on till the last guy, right? So I do compute up to this point. So instead of this guy, now I have the gradient of loss with respect to y hat, which is going to be the partial derivative of loss with respect to y hat 1, partial derivative of loss with respect to y hat 2, and so on till partial derivative of loss with respect to y hat 8. OK? Then I'm going to just put it back in the form that I did before, I had before flattening. So it means that y hat went here. Now this partial derivative is going to be here. You got the idea? So this second partial derivative is going to be here. The third one here, and so on. The last one is going to show up here. Clear? Now, this is another representation of the same loss. And I'm the same gradient. And I'm going to call this one the gradient of loss with respect to tensor y hat. OK? So when I say gradient with respect to tensor y hat L, I simply mean that I got that one, and I did the rearrangement to be shown as in the form of the tensor. So I haven't done any computation. It's just rearrangement. Clear? So I just rearrange it. And now the only thing that I need to know is that how can I move backward or do the backward pass through the pooling layer and also the convolutional layer, because once I do know that, then everything is clear for me. I can move backward to the very beginning. Right? Everybody's clear? Yeah? Great. So let's start with the max pooling. So let's do the pooling first, because that one is the easy one. Say I have this particular example. And what is happening in this example? This is just a max pooling over 3 by 3 input. And if I want to do it, I just look at this filter and I take the maximum value. OK? Say, for example, here in this example, so the maximum between these 4 values is y2. So this is what you see here. So as I told you, I'm going to write down the index also here, right? So I keep index 2 as well there. Then I go for the next window, say again in this one, y2 is again the maximum one. So I'm going to put at the output of my max pooling layer, it's going to be y2. And here the index is 1. Clear? Because in this filter now it is the index 1. Correct? I go for the next one, say here is y7. So it means this is the guy. So the index is going to be 3. And then for the last one, say this is y9, the maximum one. So the index is going to be 4. OK? Now, what I do assume, I want to do backpropagation. if I want to do backpropagation over max pooling layer, what do I have? What kind of gradient do I have? The gradient of loss with respect to which map? The green one or the blue one? The green one, right? Because I do see the gradient with respect to the pooled one, correct? I want to get back from the pooled one to the input of the pooling, right? So I do have the gradient with respect to this y hat, to this map. Now I want to compute the gradient with respect to the input map, okay? So let's do it together. So what should I do if I want to compute that gradient? Chain rule, of course, right? So let's use the chain rule together. So let me just write down one of them. So say I want to compute the partial derivative of the loss, or this r hat, with respect to y1. So let me just look at it. y1, the first entry in the input, in the blue map. Okay? I want to compute the partial derivative of my loss r hat with respect to y1. So if I want to use chain rule, what should I say? One thing that I can say, I mean, I do know this is not exactly the case, but it's not going to harm. I can say everything at the output of that output map, everything in this green map, is a function of y1, right? Because that is computed from this input. I mean, I do know that some of them are not going to include y1 definitely, but it's not going to harm me if I assume that, right? So if this is the case, then I could say, OK, I'm going to compute the partial derivative of r hat with respect to y hat 1, which is the first pooled entry. And then I multiply it with the partial derivative of y hat 1 with respect to y1, right? Now, should I add any other term? I'm going to go for every single guy in that green map, right? So I'm going to say, OK, the next one is that I compute the partial derivative of my risk or loss with respect to y hat 2. And then I see what is the partial derivative of y hat 2 with respect to y1. And I keep on going till the last one, right? So here, I mean, you have only 4 terms. So the last one is going to be r hat with respect to y hat 4. And then it's going to be multiplied with the partial derivative of y hat 4 with respect to y1. And my y1 could appear only in y hat 1, y hat 2, y hat 3, y hat 4. As long as I write down like this, I'm totally safe. Correct? Yeah? OK. So great. So I'm going to write it down in this form. So every particular y hat, I'm going to just apply the chain rule on it, and then I sum them up. But if I do it on y1, it's going to be 0. Because y1, just look at this example. I'm just doing it for this example. y1 is not showing up anywhere, correct? None of these y hats is y1. None of them has y1, right? So it's going to be 0. What about y2? What happens if I just consider I want to compute y2? So everything here is going to change instead of y1, y2, right? So everything is as before. So y hats are the same. The only thing is that this one is over y2. Now y2 shows up where? Where does it show up? Here and here, right? So it's going to show up for y hat 1 and y hat 2. And what is the derivative of y hat 1 with respect to y2 or y hat 2 with respect to y2? It's always 1, because you always take the maximum guy, right? So it's either 1 or 0, correct? So all of these derivatives of y hat with respect to y, all of them should be either 0 or 1, and then you pick some of them. And which one you are picking? The ones which show up in that index map. Okay? So you can do it for for y3. You can just do it for everybody. I mean, just go ahead, y3 till y9. And then you can see that some of them are simply 0 because that y is not pulled out. And some of them having some components, which is summation of multiple derivatives of y hat. Okay? But this guy is not a very visual thing, so let's do a bit of visualization. So let's look at this guy. And I want to just compute the derivative. So what I'm going to do, I'm going to put the gradient in the form of the output map. Okay? This is the gradient that I do have. And I want to compute the gradient at that part. Right? So now, what I'm going to do, I'm going to look at this index. And this index tells me for the first entry, the index when you were max pulling was 2. Meaning that in this filter, which guy I had taken in the max pulling? This one. So I'm going to put it 1, everything else 0. Right? Clear? Now, I'm going to multiply this one with this guy and then put it here. Okay? Clear? Now, I go for the next one. For the next one, the index is 1, meaning that inside this filter, this guy was taken, this one. And then I just multiply it with this guy, and then put it exactly the place that I had pulled out, right? And if there is anything there, I'm going to sum up with that. Clear? For the next one, the index is 3, so it means that I should put 1 here. Anything else is 0. And then I multiply this guy with this map, and then I put it here. And same thing for the last one. Okay? So now, what is happening is that if I have that output map with gradients or partial derivatives in it, I just need to make these filters, and then I multiply here, and I copy here. Yeah? And if there is anything there, I just sum up. So it's a kind of inverse form of convolution, right? It doesn't wonder, I mean, it's not, doesn't surprise anyone because the pooling itself is a kind of convolution. So we're doing an inverse or reverse of convolution. But a better thing is when we just do mean pooling. Okay? That's going to be even more intuitive. Because if I do mean pooling, I told you this is basically that I assume I have a filter, a uniform kernel, a uniform filter, and I'm just sliding it over the input, right? So I'm just averaging these guys. It's going to be y hat 1, averaging the next ones, y hat 2, and so on till the last one, right? Again, I do have the gradient of this green map. I want to just compute the gradient of this blue map. The thing that I'm going to do, I'm going to use the same chain rule as before. And now, what I'm going to say, OK, let's compute the gradient with respect to y1. So it's going to be the partial derivative with respect to every single pooled entry divided by the partial derivative of that pooled entry with respect to the y1, right? And now, if you look at this guy, OK, for y hat 1, does it include y1? Yes? So y hat 1 here, y hat 1 is simply y1 plus y2 plus y4 plus y5 divided by 4. Now, what is the partial derivative of that guy with respect to y1? 1 over 4, right? So it's going to be 1 over 4. You see here? Now, none of those other y hats include y1. You see? y1 does not show up in any other filter, meaning that all of those partial derivatives are going to be 0. Yeah? So what about y2? I'm going to do the same thing, right? But this time y2 is going to show up in y hat 1 and y hat 2. And because of that, it's going to just have both of the terms. And every single term has partial derivative 1/4, so I'm going to multiply it. Clear? So you can keep on going for every single one. The one which has the most terms is y5. And this is because if you look at it here, y5 is always there. You see it? So every single time you are doing the pooling, y5 is there. So every single y hat you compute, it has a bit of y5 in it, right? And because of that, y5 is going to include all of them with coefficients 1/4, right? And then you can just go on and complete the whole chart. Yeah? So again, you can look at it the same way. So you could say, there in the max pooling, I told you, like, put 0 and 1 for the filter. No, you just put this uniform filter, and then you multiply it there, and then you copy it there. Okay? And then again, you go next. You again multiply this to that one, and put it there. If there is anything, you sum up with that. And you keep on going till you just scan the whole thing. Okay? But the whole cool part is that you actually don't need to do this. You have even a better visualization. And what is that visualization? If I just get this guy and zero pad it all around, okay? And then I take this filter 1/4, like uniform kernel, and then I convolve it with that guy, I am going to get exactly the things that I showed you. Okay? I mean, we are a bit out of time, so you can try it at home to show that this is the same thing. But if you do it, you're going to see exactly. I mean, just look at this first term. So in this first term, I have done zero padding, meaning that every guy here is 0, right? So the only thing that is going to show up is 1/4 times this guy. So this is exactly the thing that we computed for y1. Okay? For the next one, you're going to have 2 terms, right? For the next one, you have only 1 term, 2 terms. For y5, we have all of them, right? It's the correct one, right? And if you go for the last one, you have, again, only 1 term. So better visualization, when you are doing backpropagation, you're simply, again, doing convolution. Yeah? So you get your gradient. So moral of the story, if you are doing pooling, when you want to do backpropagation, you basically get the gradient of the output, and then you just modify it a bit. I mean, here that is very easy. You just add a bit of 0 around it. And then you're going to go for a convolution type operation. Like in the mean pooling, you basically do convolution. OK? So, yeah. So that's it. So for the backpropagation over convolutional layer, I'm going to do it, yes, of course, after the reading week, unfortunately. So I cannot finish it here. But just give you, I just want to spoil everything for you before you, because I know you cannot just enjoy reading week if you don't know what is going to happen. So the thing is that the very nice thing about convolution is that when we do backpropagation, we're going to see that the backpropagation of convolution is again a convolution. So when you want to do a backpropagation, you just modify the filter, meaning that you have, say, for example, k different filters, and every single of them has c different channels. Then you just resort them into c different filters. Each of them has k different channels. And then you get the gradient of the output. You just convolve it with that new modified filter, and then you get the gradient of the input. And this is one great thing, because it's going to make the forward and backward propagation of the same form, make it very easy to implement and very efficient. Okay? So we're going to see it in the, on second next Tuesday. Okay? So I hope you enjoy reading week. I am going to upload the assignment 3, but I am going to give you extra time because I don't want to make you work during reading week. Okay?